Hello everyone, welcome to third episode from Extreme Loading for Structures software. In today's episode, we will be speaking about progressive collapse analysis as well as the user-defined reinforcement rebars. Let's get started in here by checking the outlines for our episode. In the beginning, we will be discussing what is progressive collapse analysis. Then we will move to ELS verification example to prove that the ELS is very good tool when you are doing progressive collapse analysis. And third, we will be doing a live example that shows a building, a four-story building, and we will be removing a column from the bottom floor and see the effect of the removal of the column. Let's begin by defining what is the progressive collapse. Progressive collapse, as the code describes it, it is a process where a primary structural element fails, resulting in failure of adjoining structural element, which in turns cause further structure failure. In other words, it's basically when we remove a structural component like a column or a bearing wall and we check if the building is going to bridge over this removed structural element or not. If it's going to bridge over, then we are seeing only large deformations and deflections. If it's not going to bridge over this missing column, then we will be seeing a failure that happening in the building, and this failure is going to propagate through the building. As an example, we are showing here the Oklahoma building that collapsed in the 90s due to a terrorist attack. In this example, we will see a blast load that induced a failure in these columns, the columns here at the front of the building, leading to the progressive collapse of the components of the building. So let's play this video. We are seeing here failure in these three columns, leading to the partial collapse of these bays and these structural components inside the building. So, as a designer, you have to check if the building is going to bridge over this missing support or this missing structural component or not. There are many codes that speaks about the progressive collapse analysis, but the most famous one is the UFC code, which is UFC 40203, design of buildings to resist progressive collapse. And actually, the code describes two methods for the designer to use to do a progressive collapse analysis. The first method is an indirect method, which is called the tie force method, where the designer has to make sure that there is a continuity in the load path for the tension loads in the floor as well as in the columns and as well as in the beams. Either they are the peripheral beams or interior beams inside the building. We will not be speaking about this method that much because it is an indirect method and usually it causes like large cross sections and it is not very economic when you are doing progressive collapse analysis. The second method, which is the alternate load path method, where the engineer or the designer has to remove a primary structural component from the building and then check if this building is going to fail or not. And the failure here is not described by like a failure and visual failure in the building. It is there is like some acceptance criteria in the code that you can return for. The first one, very quickly, is deformation control, where you have to check if the plastic rotations at the beams here are within the code range, or the force control if, for example, these beams are going to be safe in the shear or not. Let's go ahead and see the advantages of using ELS software in doing a progressive collapse analysis. Of course, we are using a nonlinear structural analysis method with using nonlinear material models. The plastic hinge formations are automatic, as we have discussed in the first introduction about ELS software. Membrane action and P delta effect is already included in the analysis in an exact way. We will also be seeing how to extract the plastic rotation uh, calculations, as well as the debris loading and how the debris loading are going to affect the results of your analysis. Let's begin here by showing a verification example or a way to verify if the ELS is working in a good way or not. So basically what we have in here is an experiment that was done in the lab for a 2D reinforced concrete frame with infill walls, and these infill walls are connected to the columns using dowels as we see in the pictures in here. We can see here also the ELS model for this case, where we see here the geometry and the reinforcement rebars, as well as the staggering masonry, which is matching here the infill wall that we see. Now, let's check the analysis results that we got when we run a progressive collapse analysis. Basically, we removed this column and then apply a push-down analysis on the connection in here to simulate the extra loads that's added on the frame when there is a progressive collapse. So let's play the results and see how the cracking are forming in the frame. So we see here first the cracking in the masonry, then cracking here happening at the curtailment of the reinforcement, and also here some more visual way to see the cracking inside the masonry walls as well as the beams. Now let's go ahead and compare the analysis results to the experimental results in terms of the cracking first. So in the cracking here, we see here the rebar fracture that happens here at the top rebars of this beam. Also, we see here rebar fracture that's happening in here, and these are matching very well with the prediction of the ELS. We see here also rebar fracture at this location. It's visual in here and also here inside ELS. We see here a shear failure that's happened in the beam, and it is visual in here as well. And we can see also the cracking that's happening in the infill masonry walls and how they are matching with ELS results. Let's also compare in terms of load and deformation. So we are matching here very well the load as well as the deformations. So this is the deflection versus the load. So we are matching here very well with the experiment results. And then we will go through the different at different deflection. We are seeing a comparison between ELS results and experimental results. So it's visual in here at this stage. We have a deflection of around 180 millimeter, which is equivalent to what we see in here. Then at second phase of loading, we see here also the loading in the experiment matching very well with the loading of ELS, as well as in the third stage here when the failure happened at 400 millimeter, and it's shown here also as 400 millimeter. Now, let's also check here the relation between the vertical deformations versus the horizontal deformations at each floor, because these are the way to check the membrane action and how it is affecting the results of the progressive collapse. So we see here at LVDT1, which was at the third floor, we see a relation between the horizontal movement versus the vertical movement at the third floor. We also see here at the second floor the relation between the horizontal and the vertical, as well as in the first floor as we see in here. Now, let's start creating an example for progressive collapse analysis for a reinforced concrete structure. 5 bays, as we see here, by 4 bays. The distance between the columns are a 30 feet, as we can see in here. This is the columns that we are going to remove to do the progressive collapse analysis. And the height of the floor is set as 15 feet. We have here the beam dimensions, the widths and the depths. So it is 12 inch by 30 inch. columns are 18 inch by 18 inch, and the slab thickness is a 12 inch. The live load assigned on the structure is a 50 PSF, and using the UFC code load case for doing progressive collapse analysis, we will need to apply this kind of load combination, 20% increase in the dead load and half the live load only. Going to the next slide, we can see here the column reinforcement as well as the beam reinforcement in here. In this case, we are going to divide the beam into three parts. The first part, which is mainly at the corners of the beams near the column, and the beam in the center is having this cross section in here. Please note that the stirrups near the column here is set as 6 inches on center, while at the midspan of the beam it is set as 12 inches on center. Let's go ahead and start by opening ELS software. And if you remember from the last episode, we talked about setting up the model so that we first specify the first level height. So the first level height that we have in here is 15 feet. And I'm going to click OK to open up the main modeling window. Now, let's start by creating the column styles and then insert the columns, girder styles, and then we will insert the girders, and finally we will do the slab and the custom reinforcement inside the slab. So let's go ahead and start our modeling. So I will get here a 3D view and I will go to the column style. Let's first change here the units to be length in inches and mass as kips. And I'm going to the style in here and specify the column style. Column style, as we have seen, it is 18 inches by 18 inches with a material of normal concrete. And the reinforcement rebars inside, let's go back to the example in here. We have number 8 bars, and the stirrups is number 3 at 8 inches. So I'm going to put this information in here, just put the cover first, and we will put here 3 bars with number 8 area and 1 bar in the other direction because we are excluding the corner bars with a material of normal steel, and the number of branches in each direction for the stirrups is 3, spaced at 8 inches on center with an area of number 3, and apply and OK and OK. Now I'm going to insert the column. I would make the meshing for this column at the beginning something very simple. So I'm going to the properties in here, define the meshing of the column as 10 by 1 by 1. Just something very simple. We will be doing the meshing later on, and I will explain why I I want to make the meshing later. Then I'm going to copy the column from the midpoint at a distance of 30 feet, which is 360 inches. So we have created here another copy from the column. Now let's go to the girder. And in the girder, if we go back to the PowerPoint slide, we need to put here 4 bottom bars, number 10, and 4 number 4 bars at the top in here. While in the midspan, I will put 4 number 10 and 2 number 4 for the top. So I will call this beam 1, beam style 1, and this will also be beam style 1, and this will be beam style number 2. So let's begin with beam style number 1. I will call this one beam 1, and I will put the geometry 12 inch by 30 inch with a material of normal concrete, and I'm going to specify beam 1 as the reinforcement details that is at this area in here, which is 4 number 10 at the bottom, 4 number 4 at the top. So let's go ahead and put this information. It's 4 number 10 at the bottom, and on the top it is 4 number 4, and we will put one sidebar in the middle. Let's put it number 3. And then for the stirrups, we have two branches of stirrups at each direction with a spacing of 6 inch, because this is the stirrups near the connection, with an area of number 3. Apply and OK and OK. Now let's go ahead and do also beam style number 2, beam 2. So I have here two options, either to create a new geometry for the beam, or I can use girder geometry 1, since they both have the same geometry and the cross section. So I have chosen here to use girder geometry 1. As for the reinforcement, we have 4 bars number 10 in the bottom and 2 bars number 4 on the top, with one sidebar as well, with an area of number 3, and the material of normal steel, while the stirrups here are two branches of stirrup spaced at 12 inches on center with an area of number 3. And apply and OK. Now I want to draw the new beam starting from the face of the column up to the end, which is basically 1/3 of the length of the distance between the columns. So what I can do here is to draw a draft line starting from the end of the column, and just to specify here the distance or the length of this draft line, as we can see in here. So this is a guide for me to put the beam starting from the face of the column up to the end of this line. And I can go ahead and draw it like this. Draw the girder, and remember that this is beam 1 style. And I can do the same thing in here for the other line or the other column, and I can make a spacing here at -90 and 0. Oops, seems I typed it in a wrong way. Let me type it again. Draw a line from the midpoint of the column at -90 and 0. Now this line is having a length of 90. And I can do the same in here. I will do the start of the beam from here, ending here. Now let's go ahead and change the style. So I'm going to put here beam style number 2, set it as the default, and then I'm going to draw the beam style from the end of this beam to the end of the other beam in here. Now let's stop here for a few seconds and try to figure out about the extension of the reinforcement. I will just go ahead and close here the reinforcement bars. I will just hide them to be able to explain what we are going to do. So basically, at this surface or at this interface between beam number 1 and beam number 2, I only need continuity of the bars. I don't need to duplicate the bars coming from this beam to this beam. The best way to do this is to select this beam, which is at the corner. Let's make it like both beams at the corner. And then I will come here at the reinforcement extension at the end of the beam and make it with a negative value. Let's put it -1 inch. This means that I have no reinforcement rebars that are going to be generated in here between this beam and this beam that's coming from the beam at the edge. Now for beam number 2, what I'm going to do is that I'm going to extend the reinforcement rebars in this beam. Let's show them first. I'm going to extend it inside this beam for the value that I have subtracted from beam number one. So I made the extension as -1 previously. Now I will make it as 1, so that I have here an extension only that's going from this beam to this beam, while this beam, the reinforcement rebar, stops and it doesn't go inside this beam, so that I don't have a duplication for the reinforcement rebars. Now let's go ahead and also try to do some very simple meshing for this beam. So I'm going to show the beam as solid and shrink elements. And now let's make the beams at the corner here. Let's make them with very simple meshing, 5 by 1 by 1. And for this beam, I'm going to make it 10 by 1 by 1. Remember that we need to check also for the extension of the reinforcement rebars need the column near the column end in here. So basically what I'm going to do in here is that I'm going to show this column or the whole thing. Let's show it as a wireframe. As we can see here, there is extension of the reinforcement rebars inside the column. But remember that we are having a continuous beam. So if we extend it all the way to near or like after the midpoint of the column, and the other beam is coming from here, so we will have a duplication in here. So what I need to do is to make an extension here for the reinforcement rebars. If I have this column as 18 inches, so 9-inch will be enough from here. And then when I copy this beam to the other side or mirror it, then we will have also an extension of 9 inches, as we are going to show later on. For the one in the end in here, I need it to be all the way to the end. So I'm just going to select this beam and change here the reinforcement rebar extension at the start to be 18 inches. Now it's time to replicate what I did in here, or we can start like taking an array command for a distance of, or two copies at a distance of 360 inches. And now we can go ahead. For simplicity, I'm just going to take a copy from this beam, from those beams in here. I can take a copy it from this point, and I will insert it at the same location. Now I can use the rotate command, rotate it 90 degrees around the z-axis for the center here, center point in here. Probably I needed to make it in the other direction, so let's make it again. Rotate -90 degrees, and we can select the midpoint of the column. Let me just get a wireframe mode. It will be easier. Maybe a plan view would get us, yes, this one. And okay. Now we have this beam with the extension of the reinforcement rebars, and everything looks fine. Now let's go ahead and show again the beams, and I'm going to take a copy from this beam from the end of the column in here to the end of the other column on the other side. Now it's time to create the slab. The slab, it is a 12-inch thick slab with bottom reinforcement rebars number 4 spaced at 12 inches on center, while for the top reinforcement, it is also number 4 at 12 inches on center, but only it covers 1/3 from the span in both direction. So I'm going to go ahead and go to the style, and in the slab this time I'm going to define only the geometry of the slab, 12 inches, and then I'm going to the reinforcement rebars. This time I will choose not to put any top reinforcement inside the style. I will just use the bottom reinforcement to create the bottom mesh, and I'm going to specify the area. It's number 4 in both direction. And for the top reinforcement, I'm going to create it using the draft lines. I'm going to select here to create a beam or a slab. We can also hide the reinforcement rebars for now. So I'm just snapping here on the corners, right click, and we can see here the slab bottom reinforcement as well as the meshing that we have. Now, if we go ahead now and check here, we will find that there is an intersection between the beams and the slab as well as the column. Even if you check integrity in here, you will find that some girders are intersected with the slabs, and also you will find here that the columns are intersected with the slab. The best way to do this is to just check intersection, like integrity problem here. If we click here on OK, the ELS will automatically cut the elements in the slab so that it is at the edges right as we want it inside the model. The only drawback in this method is that you will not be able to modify the mesh anymore using the properties. If you want to modify the mesh, you will have to select all the elements in the slab by selecting all elements, and then you can do from the right click here, you can do remeshing for those elements. And I'm going to show you the steps of doing this while we are refining the mesh at the areas where we are going to do the progressive collapse analysis. Back to our model in here, I want now to create the top reinforcement for this slab. Very easy. I will go to the draft layers. I will create a new draft layer. Let's call it top reinforcement. And I will give it a color. Let's choose this color in here, apply and OK, and let's make this one as the active layer so that any line that I draw, it's going to be with the layer that's having a top reinforcement. Now we can hide also the reinforcement or the lines which was the draft, the original one. And I will begin by creating, I want some reinforcement rebars starting here from the edge of this beam up to the edge of the other beam. So I will begin by drawing a line in here starting from this point at a distance of 90 inches in X direction and 0 in the Y direction. So I have here my first line. Then I need to replicate this reinforcement rebar all the way to the end, spacing at 12 inches on center. So basically what I'm going to do, I'm going to use the array command in here. The number of items, if we calculate it in a good way, so we will need 29 rebars with a distance between them as 12 inches, and press on OK. So we will find that we have created the reinforcement rebars in here. Now, with the same exact concept, I can create the other areas of these rebars. However, it will be much easier for us if we select these lines in here, 29 lines. And as I did with the beams, I just copy these lines from a point here to the same point, and then I'm going to rotate it 90 degrees around the z-axis at this location. Perhaps I need it also to be in the other direction, so undo minus 90 along this point. Let's go ahead and move these lines from here to the intersection between the beam and the lines. And also what we need to do here is to take a copy from these lines, and this time we can use the mirror command. So I'm going to mirror these bars on the other side along axis xz. Let's choose the midpoint of this beam, and we have those lines in here. Same thing here. I can take a copy from those lines, or same like the array command. We have chosen two more bars, I think. Let me exclude this by click on Control. So 30 lines, we still have one more line to remove, which is this one. And now I can make a mirror. Oops, let me choose this again. "29 lines, mirror along YZ plane." We'll choose here the center of the slab and click OK. Now we have the meshing already in place. I'm just going here to select all the lines and shift them to account for the cover. We have here the cover as 1 inch for the slab. So I will shift these beams down minus 1 inch. And then from the additional task menu in here, I'm going to go to convert draft to general RFT, select the area, so number 4, with a material of normal steel and no pre-stressing force, so okay. Now we can hide all the draft layers and we'll find the reinforcement rebars in place. Now what I need to do is just to make like a copy from what we have in here, array it, or use the copy command to create the other base. So I'm going to select the copy command, and I'm going to take copies from this frame, repeat it 5 more times. And I will do also the same thing for the other side. Copy, copy from this point to the end point and repeat it 4 times. Now let's check one more time if we have any integrity problems. So we see here that we don't have any integrity problems. Now it's time to define the loads on the slabs here. What I think, or what we should do in here, to do a dynamic nonlinear analysis, you need to assign the load either as a lumped mass or as a in the specific weight of the material. So if we go here to the material and the material of the normal concrete, we'll find that we specify here the specific weight of the concrete. So I need to create a new material. This material is going to be for the slabs only because the loads are on the slabs only. We are going to put our load in the form of a specific weight, and I'm going to show you how to do this now. First thing, we need to create a new material for the slab because this is where we are going to put the live load and the dead load on the floor, apply, and OK. And I'm going to change the units here to be as feet and as pounds, just to make it easier for us to see values in a better way. So the first thing we need for the dead loads of other components other than the slab, to be multiplied by 1.2 to account for the load case that we have in here. 20% increase in the dead load. So the dead loads here, 156, 156 times 1.2 give us 187.2. And this is what I'm going to do in here. And then for the slabs, which will have the loads here, I'm going to calculate the on weight plus the live load. So we have the live load as a 50 PSF, and I'm going to calculate now, or convert it to a pound per cubic foot. So to do this, we have a 50 divided by the thickness of the slab, which is 12-inch, divided by 12 because we are working in feet here. So this gives us a 50. Multiply it by 0.5 because this is the live load, and then add 1.2 times 156, which is the cubic weight of the material, gives us 212.2. And this will be basically the load on the slab. Now it's time to select all the slabs in the model and convert its material to be as a slab. Just right click here on the slab components, select all the slabs, then go to materials here, convert these all to be slabs as we see in here. Now it's time to do the meshing or refining the meshing. Basically, I will be removing the column in here. So the first thing I need to do is to select all the columns that are near the area where we are going to remove the column. And I'm going to refine the mesh for the columns in here. Let's put this as height 30 by 3 by 3. Of course, same for this one to account for the connection. So 30 by 3 by 3. And now for the beams, we can select all the beams here, all the edge beams. Probably we need to hide the slab because it will be much easier for us, and also hide the reinforcement rebars, and make selection for all the edge beams near this area. And I'm going to change its meshing to be 10 by 1 by 5. And same thing I'm going to do for the beams at the mid span. I'm going to put them as 15 by 1 by 5. So now I have refined the meshing for the columns, the beams. Now it's time for the slab. And the slab, as we have discussed before, its meshing now is locked. So I will teach you now how to change the meshing for an area of the slab that have a locked mesh. Basically, for the slab, I'm going to select one element from the slab and then select all the elements in the slab. Then go to the additional task menu, remesh selected elements, projection A, which is this one, and I'm going to define the slab as 30 by 30 by 1 element through the thickness. And now we have refined this one. Now it's time to refine the other one. Select all elements, same exact steps, and then I'm going to remesh selected elements, same projection, 30 by 30 by 1, and we have defined it right now. And it is still having here a material of a slab. Now it's time to do the array. I'm going to array, so I'm going to copy this level, and then I'm going to array this level 3 more copies. And now the model is ready for assigning the load uh, case, which is a dynamic analysis, and the columns that's going to be removed. So basically, we need to go to the loading scenario first and define a new loading stage, which is a dynamic with a load condition of concentrated load and a time step of 0.01 and a step division of 10. This means that our actual time step is 0.001, and I will click apply. I don't need to assign any loads to this load case because the loads are already embedded in the material properties of the components that we have in here. So I just need to see the effect of the removal of the column on the structure that the loads are already applied on in the material. Now it's time to assign the columns that's going to be removed. If you go to demolish construct scenario, new group, this will be demolish. In the stage, I'm going to remove it by stage or by time. So if you need to remove it by time, like at a certain time, you can do so. But now we are choosing to remove it by stage. Stage 2 dynamic. So this will be at the beginning of stage 2. And then I'm going to select the elements that are going to be removed from the analysis. So I'm bringing here an elevation view, then I'm going to rotate around z axis to be able to see the column that's going to be removed, which is this one. And then I'm going to click on enter and assign. Now we have here the column that has been assigned to be removed. And if you go here to the processing, you will find here in the demolish construct the column that's going to be removed. Now, one final step is to assign the material properties that we have. So let's get our units back to kips and inch. Maybe this is better for better understanding or for better seeing the units in a familiar way. So we have Young's modulus, shear modulus, we have the specific weight, and we already talked about this. The maximum compressive strength is set as this value, the maximum tensile strength is set as this value, and click OK. For the steel, we are going to use a 60 KSI steel, so I'm going to use here 60, and F ultimate of a 75. So this means that our ultimate to yield ratio would be as 1.25. So I'm going to put here 1.25 and apply and OK. Now it's time to run the analysis. Basically, what I'm going to do is to run the analysis on here, but I have already ran this analysis before. It should take around 47 minutes to finish the analysis up to the end. And when I mean to the end, like up to a 1 second of a a duration in here. I have here the output, so I'm going to open the output direct. As we see here, this is the same model, same exact configuration, and I'm just going to play the results and see what's happening when we removed the column. So we see here some deformations happening. Perhaps we can increase a little bit the scale to be able to see the deformations in a better way. So we see the column is vibrating, or the floors are vibrating. Now, the first thing that we need to check is the deflection. How much deflection do we have? So basically, I'm going to select an element from the column in here, and then I'm going to put a chart. This chart is showing the time on the x-axis versus the element displacement in z direction, and click OK. Now we see the vibration of the floor. The maximum deformations happened was 2.7 inches, as we see in here, and it is vibrating. Usually the UFC code, like, you are good up when you reach to this point and rebound. You don't have to continue the analysis up to the end. But I'm just continuing here the analysis up to the end to show you that the floor is vibrating without any uh, collapse happening. Now it's time to check the other results that we might need. So according to the UFC code, you need to check for the plastic rotation happening in those beams at each floor. The way to show the plastic rotation is basically we need to plot a relation between the rotation inside the beams versus the yield that's happening inside the reinforcement. To be able to do this, I'm just going to structures here, and I'm going to hide the floors up, and I need to draw a chart showing the rotation uh, on the x-axis versus the stresses in one of the rebars that's in here. Let's check first if we have any yielding in the rebars happening. So as we spoke before, if we go to preferences in here and then read spring states, and then we are going to show here the yielded springs, and perhaps if we bring a wireframe mode and remove the ground, I will be able to see the springs that are yielded. So we have yielding here in the reinforcement rebars in the beams as well as in the slab itself. So let's check one of the rebars in here. Let's, for example, take this rebar, and I'm going to draw first a relation between the spring stresses and strain to be able to see the load or the stress and the strain relationship for this bar. We can also check one other bar near the connection in here, near the connection of the column. So I'm selecting here another one just to make sure that we are not exceeding any values, or that is yielding at the right uh, moment and the right forces and deformations. So we see here that the yield happened at 60, and then the strain reached to up to 0.016, and then loading and unloading with the vibration of the floor. The next thing is to go ahead, and I'm going to show here through the contours, the kinematic settings. I'm going to show here rotations around y direction or y axis, and I can calculate all the limits in here, and let's get here the values in. So the default values are in degrees, and apply and OK. perhaps we need to change the units here of the angles to be radian to be much easier. So we see here deformations or the rotations, the maximum rotations that is occurred here is 0.0112. Now I can go ahead and plot a chart between the spring. So I'm going to Windows. We have one of the charts for the springs. I can use the same one in here, edit chart data. On the x-axis, I'm going to put the rotation, element rotation, so element rotation around y, and I'm going to pick this element because this is the element where we have the maximum rotation versus the stress in the bar, the normal stress in the bar. So we see here the difference between the elastic rotation and the total rotation and the plastic rotation. Basically, the plastic rotation is starting from here up to here. The total rotation is starting from 0 up to the end here, while the elastic rotation is only starting from the end up to the point where the rebar started to yield. So this is basically how we get those values of the plastic rotation. Perhaps a slide here would show it in a better way. So we have here the total rotation, we have here the plastic rotation, and you need to make comparison with the code to make sure that the plastic rotation doesn't exceed the values in the code. Using the UFC code, you have to do some calculations to get the acceptance criteria. Either it is a primary component or a secondary component. You have to do some hand calculations to be able to get to the acceptance criteria. So I did already these calculations before, and I found that the acceptance criteria is a is that the rotation doesn't is not more than 0.025 radian, and this is what we have in here. The plastic rotation calculated from ELS is 0.0112 radian, as we have seen in before. Now it's time to check for the force control, or if there is a shear failure that's happening inside the beams. So basically, you can go ahead in here and try to or go ahead and plot a shear force diagram for these beams in here. And remember that ELS is the only software that's using a solid element analysis, and yet you can get values for internal forces diagrams like bending moments and normal forces and shear and so on. So I'm going to check here the shear. We see here the shear in the beams. Perhaps we can get here like a view like this, and the user just need to be able to see if the maximum shear value has exceeded the values of the shear capacity of the beam. Let's go ahead and go here to preferences. I'm just going to close read the springs states because it's somehow making the viewer slower. So we can see here the shear force diagram. Beside the shear force diagram, we can see the envelope. So I have here the envelope, and I'm going to turn off showing the text for the original shear force diagram, and I can see here the values, the maximum shear values that you need to make shear check for or check shear for it. So we have here the maximum value as 87 kip at the connection here near the column and the beam. You can also plot a relation between, for example, the time and the shear force in the beam. This can be done by going and showing sections that we originally created for doing the bending moment diagram. So I'm going to charts, And in the charts, I'm going to plot a relation between time, and this time I'm going to plot the straining action, which is shear 3. So shear 3, selecting the section, which is this section. I just need in the beginning to be able to select the section. And we can see here a relation between the time versus the shear in the beam at this section. Now, we need also to be able to check the axial forces that's happening inside the columns, because the columns here you have to check if the removal of the column is going, or the excessive forces coming on the column due to the removal of the column in here is going to be sufficient or not. So the way to check the axial forces in the columns, we just same thing. I'm going to plot or to show here the bending moment, or the normal forces in the columns. I'm just going to turn off the beams now, just to be able to see what's happening, and we don't have interactions between the diagrams that we have. And let's go ahead and select the column in here, and plot a normal force diagram for them. We see the normal forces, and we can play a video. We see an increase happening in the normal force when the column has been removed. With the same exact concept, I can plot a relation or check the envelope. So we have the envelope in here, envelope text, and then hide the original text. We see here that the maximum force obtained is 754 kips. We have here the units as scientific, but if you want to change these units to be numerical, you can change it here from the preferences, and we have here the value in kips. You can compare these values to the value of the code for a reinforced concrete beam. I mean a column. Now let's do another trial in here. I'm going to select all the beams here at the corner or near the connection of the column, and I'm going to change the spacing of the stirrups in there to be at 12 inches on center. This is what I'm going to do now. Here, instead of having the spacing as 6 inches, I'm going to put the spacing as 12 inches on center. And then I'm going to do the analysis again. I've done also this exercise before, so I'm going to show you directly the results. Let me begin this from the beginning so that we can view the results from the beginning. And in this case, let's play the results and see what's happening in the frame. So we see here a shear failure that's happening at the beam. And this is like correlated with like the way or the need of increasing the the spacing or having more stirrups near the connection in here. So we see here a shear failure. Now, something here I want to show is that if you plot a relationship between the deformations, let's let's plot here a relationship or a chart between the time and also the element displacement in z direction, and click on OK. We see here that the beam started to rebound a little bit until the shear failure happened. And when the shear failure happened, we see here that it goes all the way up to a 16 inch. and then it rebounds again. The reason of this rebound, I'm going to dis- discuss it with you now. Although you are having here a shear failure, but remember that this software or ELS software is capable of considering the P delta effect as well as the membrane action and the catenary actions. So let's go ahead and show here. The first thing I'm going to show is the cracking. How much cracking do we have? So I'm going to show a relation, a plot for the strain contours, and let's go here to the beginning. So we see here cracking happening. Let's hide the upper floors. So I'm showing only now one floor, and let's play the results and see what we have got according to what we see here in the chart. So we see here as soon as the shear failure is happening, we see failure, diagonal cracking in the slab, and then the beam started to work in the catenary action mode. Like the beam now is carrying a tension, and this can be shown in here if we plot or show. Let us hide the slabs for now, and let's go ahead here and show the normal forces in those beams. Normal force, and then start from the beginning. And also I'm going to put the chart next to the animation. Let's put this here, and let's see what's happening in the beam. So this is the normal force, and now we see that the catenary action and the membrane action is developing, and the beam could survive the progressive collapse. But it is surviving it in reality. But according to the UFC code, this is considered as a progressive collapse case. Like you need to make a strengthening for these beams to so that you don't have a progressive collapse. But even if you have something like this happening in the field, don't worry, the building is not going to fall down or collapse. You still have the catenary action working, and it's going to be able to carry the the um, the excessive loads coming from the removal of the columns in here. Some other cool features that we can show here is the filtration option. Let me show you what is the filtration option. Suppose that I want to show the reinforcement bars on those beams that yielded, and I want to color them in a different color. So I'm going to open here the browser and then go to filtration. In filtration here, I'm going to pick springs, add new filter. In this filter, I want first to put the spring material, which will be the reinforcement rebars, which is the normal steel. Generate spring material equal normal steel. Then I need to specify a, a stress value. So I'm going to check here normal stress in the spring and generate. I also need this value to be greater than or equal to 60 KSI, which is the yield. And I want also to put these values for the beams only. So I want to check these for the beams only. So object type, generate. Object type will be girder. And I want this also to be in the first floor only. So go here to the floor or the level, generate at level 1. Then I need to make like a common thing between them, and or. So there is an and or. So I'm going to put all these inside the box. And also for the generated springs here for that is going to be shown, I want them to be shown in a red color with a length factor of 1 and a width factor of 5. Let's click on apply. It might take some time to generate or to go through the all the springs in the model and make the filtration for them. So now the filter has been activated. Now, if we go ahead and play the analysis, we should find the springs that are yielded in the beams shown in here. So any spring that's having a material of normal steel and is having a stress greater than or equal to 60 in the first floor in the girders, it's going to be shown in here. You can see here also the yielding happening in the bottom reinforcement of the beams. All right, I think that's it for the third episode. I hope that you find this information useful, and please don't forget to subscribe and share with others to share the benefits. Thank you.